All right, this is the last chapter that I will do in the summary of the first semester. Strap in, this is the longest chapter. We have quite a bit of work to do, but this is it. Once you get done with this one, you'll be done with semester one. All right, the topic of this chapter, let me pop back, is parallels. Um, all kinds of results that follow from the behavior of parallels. Perhaps the most notable of these results will be finally the triangle angle sum theorem. We will prove that the sum of the angles of a triangle is 180 degrees, but we do have quite a bit of work to do before we get there. So let's begin with the concept of an exterior angle. Now here in this review, I won't actually take the time to uh, construct any proofs that make use of this idea. But still, this is an idea that does arise throughout the remainder of the year, so we do need to talk about it for a little bit. And again, it's exterior angle. So imagine that we have in front of us a triangle, or it could be a polygon with more than three sides, but we'll consider only triangles here at the start. And what we do is this, is we extend a side through a vertex. Okay, so just, of course, each side is a segment, and a segment is part of a line, so just simply produce more of that line. Now, when you do so, you create an angle that is a linear pair with one of the triangle's interior angles. When you do this, that's an exterior angle. So if you were to look at the diagram that's at the bottom here, we did create an extension of a side. That's the dash segment. The dash only indicates that this was in addition to the diagram. It has no other significance. And when we did this, we created an angle that formed a linear pair with one of the triangle's three interior angles. And that is angle number one. That's the angle created. So by definition, angle one is exterior. Now, of course, at each vertex, we can extend each of the two sides that meet at that vertex. And so that means that at each vertex, we can create two exterior angles. So for instance, bottom right, we extended each of the sides that come together at that vertex. We created an exterior angle 1. We created also there an exterior angle 2. And at the other vertices, we did the same. We extended each of the sides, and the result was a pair of exterior angles. Okay, so here they are, the initial angles, the exterior angles 1 and 2, and then 3 and 4, and then 5 and 6. To note here, uh, uh, to make an obvious note, if you consider the relationship between a pair of exterior angles at a vertex, like angles 1 and 2, well, clearly they are vertical angles, which means that their measures are equal to one another. And this is the reason why typically when we consider the exterior angles of a triangle, we consider only one at a vertex. Yes, another one exists at that vertex, but it is vertical to the one that we have, so those two angles are equal. Remote angle. Primarily when we talk about exterior angles, not always, but primarily when we talk about exterior angles, we talk about the remotes of a particular exterior angle. Now the definition is this. For each exterior angle, its remotes are the angles interior to the triangle to which that exterior is not adjacent. So look at the diagram below. We have the exterior angle 1, and then, of course, the interior angles of the triangle are 4 and 5 and 6. Now, the two of those to which 1 is not adjacent are 1's remote angles. 1 is adjacent to 5, so the two angles to which it is not adjacent are 4 and 6. And this means, of course, then, that 1's remotes are 4 and 6. If we move, however, to angle 2, the two interior angles to which it is not adjacent are 4 and 5. So 2's remotes are 4 and 5. And then finally, 3's remotes are 6 and 5. So note this well, each exterior angle has its own remotes, and there's no reason to suppose that the remotes for one exterior angle are the same as the remotes for another. And indeed, typically they will not be. Now, there is a theorem. We will not take the time in the summary to prove it, but it is a theorem of some consequence. It's called the triangle exterior angle inequality. I believe it's the first of our theorems, or perhaps the second, that gives us not an equation, but an inequality instead. And what it says is this, is that the measure of an exterior angle of a triangle is greater than the measure of either of its remotes. Not greater than the sum of its remotes, but rather, if you compare it first to one of its remotes, it is greater than that remote. And then if you compare it to the second of its remotes, it is also greater than that second remote. If we just go back to the picture then, that would mean in this diagram that angle 1 is greater than either 4 or 6, angle 2 is greater than 4 and greater than 5, and angle 3 is greater than 6 and greater than angle 5. Now, let's move on to parallels. That's primarily the topic of this chapter. So, of course, we must start with the definition. We must start with symbolism. We must start with a typical diagram for parallels. So here they are. First of all, we say that two lines are parallel when they are coplanar and do not intersect. Now, the coplanar part is just something that we assume in this class. This is a class in planar geometry. That is, it concerns objects that all occur within a single plane, but I did make that explicit. Parallel lines are coplanar, and also they do not intersect. Okay, no surprise here. I suspect that you knew that this was true. We do have a symbol for parallel. Of course, it would be good to have a small symbol instead of have to write out is parallel to. And that symbol looks like, I just circled it, a pair of parallel lines laid next to one another. So A, that symbol B, is read as A is parallel to B. Now, just as back in chapter 1, we allowed diagrams to tell us that segments are equal in length or that angles are equal in their measure. We can also allow our diagrams to say that two lines are parallel. And the way we do that is we put little arrows on them. So notice that line H has an arrow. Line J has an arrow as well. So the diagram has said that line H is parallel to line J. And notice that just as with hash marks used to indicate a quality of measure, we can use multiple arrows as well. So for instance, we could put two arrows on H and two arrows on J, and that also says that the two lines are parallel. Now, typically, when we talk about parallels, we always have a third line present. We don't talk about the two parallel lines in isolation, but rather we have a third line called a transversal that intersects the two other lines at distinct points. Now do note that typically, our two lines that are crossed by or cut by the transversal are parallel lines, but that's not part of the definition. The definition is simply this. A transversal is the line that intersects two other coplanar lines, whether they're parallel or not, at distinct points. So look at our diagram. We have two lines H and J. Each of those is intersected by T, and they are intersected at distinct points. So to provide some names, T intersects H. Let me start over. T intersects H at, let us call it a point. Sorry, my software is far from perfect. So T intersects H at a point A. T intersects J at a distinct point, a different point B. So T does then count as a transversal for the lines H and J. And notice that, and this will be important to us, and this is actually how we'll bring triangles into the story. Notice that we can have three lines arranged so that what counts as the transversal depends upon your point of view. Now in the diagram that you see below, the line T does definitely cross H and J and does so at distinct points. Let's call those A and B. But notice this as well. If we wished to say that H is the transversal, then we absolutely could. Well, does H cross J? Yes, at C. Does H cross T? Yes, at A. Are those distinct points? Yes. So by the definition, J could count as the transversal. H could also count as the transversal for lines J and T because it intersects both and it intersects them at distinct points. So perhaps you begin to suspect that if we have in front of us a triangle, we can count one of the sides as a transversal for the other two sides, and that's something we will absolutely do later on. All right, so let's talk now about the angles that are created when a transversal cuts or crosses a pair of lines. Now, obviously, in general, when we have a transversal that cuts a pair of lines, that will create 8 total angles. I mean, it has to, right, because it intersects them at distinct points. The angles that are in between the two lines cut by the transversal are called interior, and the others are called exterior. So in the diagram that you see, angles 3 and 4 and 5 and 6 are in between the two lines cut by the transversal, so they are interior. On the other hand, angles 1 and 2 and 7 and 8, they are outside the two lines cut by the transversal, so they are called exterior. Now, with interior and exterior defined, we can define special angle pairs, and this will be what's most important to us in our discussion of parallel lines. Consecutive interior angles are interior angles that are on the same side of the transversal. So once again, we have two lines M and N cut by the transversal T. Angles 3, 4, 5, and 6 are the interior ones. Now consider angles 3 and 6. Consider that pair. They are interior and they are on the same side of the transversal. In this diagram, they are on the left. So they are a consecutive interior pair. The second consecutive interior pair is 4 and 5. They are interior, and they are both on the right of the transversal. Now let's define alternate interior. As the name suggests, an alternate interior pair of angles are two angles that are both interior, but in this case they are on opposite sides of the transversal. That's the significance of the word alternate. So consider angles 4 and 6, both interior, clearly, also both clearly on opposite sides of the parallel, so they're alternate interior. As well, the angles 3 and 5 are an alternate interior pair. And do let me emphasize this, when we talk about consecutive interior, or we talk about alternate interior, or we talk about the other definitions that I'll give in just a moment, these apply to pairs of angles, again, when two lines are crossed by a transversal. Alternate exterior, well, you should be able to figure this out now. Exterior means that our two angles lie outside the two lines cut by the transversal. Alternate means they are on opposite sides of the transversal. So in my diagram, angles 2 and 8 are an alternate exterior pair, as are angles 1 and 7. And then finally, corresponding. Now, the definition of this is somewhat complex, and I'll allow you to read through that. But really, visually, it's quite easy to pick out a pair of corresponding angles. Consider angles 1 and 5. This is how a student put it to me one time. That student says they are in the same quadrant, one on M, one on N. They are both upper right, okay? That is, the position that 1 occupies on M is the same as the position that 5 occupies on N, so they count as corresponding angles. Another pair would be 4 and 8, another pair would be 2 and 6, and another pair would be 3 and 7. So before, we only had 2 pairs of the special type. In this case, we actually have 4 pairs. All right, now some theorems. The first set of theorems that we will consider, that we will prove, some of them together, are called the parallel tests. Okay, these are all theorems, but we will not take the time to prove the first in this summary. And each of them has the form: if a transversal cuts a pair of lines and a certain relation obtains between a special angle pair, like, say, consecutive interior, then the lines are parallel. Notice the conclusion. We conclude in all of these that lines are parallel. And that's why I call these the parallel tests. The way they operate is this: if we pass a certain test, that is, if we have two lines in a transversal and we have the right kind of relation between a pair of angles, then we may conclude that the lines are parallel. That is, we have passed a certain test, and once we have passed the test, we may then say that the lines are parallel. Okay, so the first and fundamental test says this: that if a transversal cuts a pair of lines and forms equal, that's the right relation here, equal alternate interior angles, then the lines are parallel. This is called the alternate interior angles test, or AIAT for short. Of course, we have abbreviations. We don't wish to write this out every time we use it, and the abbreviation in this case is simply AIAT. All right, so here's AIAT illustrated. So we have two lines M and N cut by the transversal T. We have a pair of alternate interior angles 1 and 2. And the theorem now says this: if the measure of 1 is the same as the measure of 2, then we may conclude that line M is parallel to line N. And as I said just a moment ago, we won't take the time to prove this. It's not really necessary in this summary. If you're curious, you can go and look at the chapter about parallels on my site, and I there guide you through the proof. But for here, we'll just assume that it's been proven. All right, so here now are the other tests. We have 4 other tests. The consecutive interior angles test, which says that when consecutive interior angles are, note this well, supplementary, that's the right relation in this case, then lines are parallel. The corresponding angles test says that when corresponding angles are equal, that's the right relation, lines are parallel. The alternate exterior angles test says that when alternate exterior angles are equal, again, equality, lines are parallel. And then finally, the perpendicular transversal test. It says that if a transversal is perpendicular to each of the lines that it cuts, then those lines must be parallel to one another. Now, let's talk about how we'll prove one of these. I think, well, perhaps we'll do 2 together. Let's talk about how it is that we would prove the consecutive interior angles test. Okay, so here's the setup. We have 2 lines cut by a transversal that creates consecutive interior angles 1 and 2. And we also are given that they are supplementary, and then we will prove that M is parallel to N. How? Well, the first and fundamental test is the alternate interior angles test. So we will use that in the proof. You may use that in all of the proofs that I wish you to do on the problem set. Okay, so let us begin the proof. We have the given. Now, how will we make use of the alternate interior angles test? Well, here's how we will make use of the alternate interior angles test. Let us introduce a name of another angle. As you see, I added the name 3. Now, the reason that I added that particular angle is that it forms an alternate interior pair with 2. And this is something, of course, we can always do. That angle was already present in the diagram. All we did is give it a name. Be careful here. This is not a construction. Okay, the construction is when you add some new geometrical object to a diagram. We did not do that. We did not add a line or a segment or a point or whatever it might be. Instead, we simply labeled an object that was already present. So let us not call this a construction. And what you do on your proofs is just simply label the diagram however you wish to label it. And so long as you have done that, we're good. All right, so let's see. How will we apply the alternate interior angles test? Well, we must prove that angles 2 and 3 are equal. Okay, and how are we going to do that? Here's how. Notice the relationship between angles 1 and 3. Angles 1 and 3 are clearly a linear pair. Dang it. Wish it wouldn't do that. I need to figure out how to make it not do that. So angles 1 and 3 are a linear pair. That follows from the given, as shown in the diagram, of course, by simply the definition of linear pair. And then what follows at this point? Well, linear pairs theorem, of course, right? So we'll apply the linear pairs theorem to what we have on line number 2. And we know then that angles 1 and 3 are supplementary. That's what the linear pairs test tells us. And now consider what we have. We are given that angles 1 and 2 are supplementary. There it is up in the given. And now we have that angles 1 and 3 are supplementary. So think of it like this. Both 2 and 3 are supplementary to 1. That is, we have 2 angles each supplementary to the same third angle. And we know from a theorem proven in a previous chapter that when we have 2 angles each supplementary to the same third angle, those 2 angles are equal to one another. So it now follows that the measure of 2, there we go again. So it now follows that the measure of 2 is equal to the measure of 3. From lines 3 and 1, those are the places that we are told that we have supplementary pairs, and we applied the same supplements theorem. And now, notice what we've got. We now have an equal alternate interior pair. And at this point, we may apply the alternate interior angles test, which says that when we have an equal alternate interior pair, our lines are parallel. So this follows from line number 4 by the alternate interior angles test. By the alternate interior angles test. Or the AIAT. And with that, the proof is complete. Sometimes I put little boxes after the end of the proof. As I think I noted previously, all that simply means is that the proof is done. All right, so let's consider the proof of the perpendicular transversal test, which says that, if we've got 2 lines cut by a transversal, that's the universal situation here, and that transversal is perpendicular to each of those 2 lines, then the lines must be parallel. Okay, so let's talk about the proof of this. And we will make use of the alternate interior angles test. Okay, so I tell you what, I'll label an alternate interior pair, and like I said a moment ago, we can always add labels in for objects already present in our diagrams. Okay, so what do we know? Okay, well, you might think that you would apply the definition of perpendicular here. You don't. Okay, the definition of perpendicular simply says that perpendicular lines form a right angle. We don't know which one of the 4 angles it would be. Okay, so we don't know, just by definition of perpendicular, that 1 is a right angle. We don't know that 2 is a right angle. However, we do know by the perpendicular lines theorem, the PLT, that when we have perpendiculars, we have 4 right angles. which would mean, of course, that angles 1 and 2 are both right. If all the angles where m and t meet are right, and if all of the angles where n and t meet are right, then of course it follows immediately that angles 2 are right. 1 and 2 are right. So that follows from the given by the perpendicular lines theorem. Okay. And then you know what's going to happen, right? We've had to do this a number of times now. It actually seems tedious at this point, but I'll go through the details again. So it now follows that both 1 and 2 measure 90 degrees. That follows from 1 by the definition of, how about RT for right? And then it follows at this point that the measure of 1 is equal to the measure of 2 because quantities equal to the same quantity are equal to one another. So it follows that the measure of 1 is equal to the measure of 2. And that's from 3 by the transitivity of equality. And we now have, like we had before, a pair of equal alternate interior angles. So it now follows that our lines are parallel. So M is parallel to N by the alternate interior angles test. And the proof is now complete. Okay, let me show you something. We've talked about constructions. We've talked about certain additions that we can make to diagrams, and we call those constructions. The two that I recall we have talked about are this. We may always construct in an angle bisector where an angle is given. And we may also construct, given 2 points, either a segment or a ray or a line through those 2 points. Now, we may also do this new construction. And if you look on the constructions page of my site, this is construction C6. Okay, and what it says is this. If we're given a line in the diagram, line M, and we're given a point not on that line in the diagram, point P, then we may construct through that point a line parallel to the given line. Well, how actually do we know that this can be done? Well, it's a multi-step process ultimately, and once I've been through this, we won't have to go through it again. What you do is this, is just simply pick a point on M, call that Q, and that just simply is a label of an object that's already present, of course, because a line just simply consists of points. And then we construct the line PQ. Okay, so here we go. That's one of our allowed constructions. If we have 2 points, then we may construct the line through them. And now consider the angle 1. Okay, that's an angle created by P and Q. So let us now construct the angle at P, as I'm about to show you, off to the right, such that, we'll call this 2, such that angle 1 is equal to angle 2. And this is simply now an application of the protractor postulate, and that's one of our allowed construction as well. If we have an angle, we can recreate at another location a second angle, or we can create at another location a second angle with that same measure. Okay, and then what I'll do with the way is I'll simply extend it backwards, because of course a ray is ultimately simply just a portion of a line. And then notice at this point that we have equal alternate interior angles. And let us call that line that I introduced N, and then it follows, of course, by the alternate interior angles test that line M is parallel to line N. Now, when it comes time for us to construct a line through a point parallel to a given line, we won't actually go through this process. We've been through it once, and that's enough. Instead, we will simply just immediately construct that line. We now know that's acceptable, and this is construction C6. All right, so let us now consider another set of theorems that are ultimately the converses of the theorems that we proved just a moment ago, that is the tests. Remember what we mean by converse. To take a conditional statement and form its converse, we simply exchange the 2 substatements, that is the given and the conclusion. So what the theorems will look like in this case is this. If such and such, that is if some condition holds, then the lines are parallel. Before we had if lines parallel, no, excuse me, let me get this right. What we had before was this. If some condition holds, of course, when 2 lines are cut by a transversal, then we may say that lines are parallel. Those were the tests. Sorry, just a moment ago, I started incorrectly. Again, in all the tests, we conclude that lines are parallel. Okay. Now, when we form the converse, instead of conclude that lines are parallel, we will be given that lines are parallel. So all the theorems that we're about to consider, the so-called consequences, have this form. If lines are parallel, then such and such. And of course, the such and such will be about some special pair of angles. Okay. And the reason why I call these the consequences is that they are the consequences of the given that lines are parallel. Okay. Now, we had a first and fundamental parallel test. That was the alternate interior angles test. We also have a first and fundamental parallel consequence, and it's the alternate interior angles consequence. And it says that if a pair of parallel lines, notice that we're given parallels, are cut by a transversal, then alternate interior angles are equal. So if lines parallel, then alternate interior equal. Now, as for how this is proven, I won't take you through the proof of it here in the summary. If you're curious about how that's done, you can look on my site at the parallels chapter. There is a section there called the consequences, and I take you through the proof there. So if you're curious, you can go and do that. But for us right now, I won't actually go through the proof. Instead, I'll simply mention the postulate that is used in the proof. This is an important postulate for us. It comes up at various points in the class. It's called the Playfair postulate, after an otherwise obscure English mathematician. Really, his only claim to fame, so far as I know, is that he had a really nice statement of this postulate. Here's what it says. Through a point not on a given line, there's at most one line parallel to the given line. So perhaps a picture to go with this. So let us say that we have a line, I'll call it M, and we have a point P not on that line. What the postulate says is that there is at most one line through P parallel to M. That is, there cannot be two or more. And no doubt you will accept that this is true. If we already had a line through P parallel to M, then we couldn't possibly construct a second distinct line through P also parallel to M. So that's the Playfair postulate. Now, the Playfair postulate is used in the proof of the alternate interior angles consequence. And again, we won't actually give this proof, but let me make sure that you're clear about what that theorem does actually say. We start with two lines cut by a transversal, as always. We have an alternate interior pair 1 and 2. And now we say that if M is parallel to N, then the measure of 1 is equal to the measure of 2. And we have other consequences as well. I don't think I'll take the time to read through these. You can do that yourself. And let us consider the proof of one of these consequences, the consecutive interior angles consequence. Okay, so what we're given is this, that we have consecutive interior angles 1 and 2. And in this case, we are also given that the lines are parallel. That is, M is parallel to N. And we wish to prove that angles 1 and 2 are supplementary. Okay, so as for how this would go, we have the given, and then line number 2. Then line number 2, we're going to do work like what we did before. Let us introduce an angle name, 3, that forms an alternate interior pair with 2. And since the lines are parallel and 2 and 3 are alternate interior, we may then use the alternate interior angles consequence to say that the measure of 2 is equal to the measure of 3. Okay, so we can do that immediately. So the measure of 2 is equal to the measure of 3. That follows from the given by the alternate interior angles consequence. And then let's ask again, like we did before, about the relationship between 1 and 3. Clearly, they're a linear pair, and that follows just by definition of linear pair. So angles 1, 3 are a linear pair. That follows from the given, as given to us in the diagram, by the definition of linear pair. And then, of course, it follows from this that angles 1 and 3 are supplementary. And of course, that's just the linear pairs theorem, the LPT. And then think about what we've got. Okay, we know that angle 2 is equal to angle 3. And we know that angles 1 and 3 are supplementary. So what then follows about angles 1 and 2? Well, here's what I wish to do. You see the occurrence of 3 in line number 4? I wish to replace that with 2. And I may do so because angle 2 and angle 3 are equal to one another. So I can transform line number 4 into this line number 5. So angles 1 and 2 are supplementary. And that follows simply by substitution. Okay, so we needed the equation on line number 2, so we could substitute into line number 4 and get our conclusion that angles 1 and 2 are supplementary. And with that, the proof is complete. Okay, so let's now begin to talk about some consequences of the work that we've done with parallels, and this will include the triangle angle sum theorem and some other consequences as well. But before we hop into that, let's have a few definitions. First of all, a right triangle is a triangle that has at least one right angle. An obtuse triangle is a triangle that has at least one obtuse angle, and an acute triangle has three acute angles. These are just definitions, okay? This must be accepted then. However, perhaps you will be troubled by the just one. Perhaps you will take this to suggest that I believe that a right triangle could have more than one right angle. Well, that's not true. But what I wish to emphasize here is this, is that that is not a matter of definition. Instead, we will prove in just a moment that a right triangle has precisely one right angle, and we will also prove that an obtuse triangle has precisely one obtuse angle, and we will be able to do that ultimately by the triangle angle sum theorem, which we are about to prove. Now, I also need to pause and talk just a little bit about proof in this chapter. Um, I know that we have given proof in a particular style up until this point in time. We have given column style proofs, but very often from here on out, I will give so-called paragraph style proofs. Now, what are these? I won't arrange the proof in column form. Instead, I'll simply write the proof out sentence by sentence. Now, that doesn't mean that like the standard here has changed. We still must provide reasons for the statements that we make. A proof is still a proof. Um, Instead, all we've done is arrange the proofs differently. Now, the reason that I do often like to give paragraph proofs is that they are more versatile. They, for instance, allow for explanatory remarks that strictly aren't part of the proof. As proofs grow more complex, it is often helpful to make some sort of remark to the reader of the proof that helps them understand it that wouldn't strictly belong in a column proof if we were to give that column proof. It's also sometimes helpful to repeat yourself. And it's sometimes helpful to say what it is that you intend to prove at a particular point in the proof. And you can't really do this if you give column style proofs, but if you have paragraph style proofs, you can absolutely insert those explanatory comments. So you will see me occasionally, actually quite often from here on out, give paragraph style proofs. Okay, so here's our first one. The triangle angle sum theorem, one of the most important theorems of the entire year. And our abbreviation for this is TASTY. T from triangle, A from angle, S from sum, T from theorem. And then theorem also has a couple of E's in it as well, and I pulled those two, and that gives us TASTY. And I absolutely love that name for this theorem. It is a tasty little theorem. So we are given a triangle ABC, and we wish to prove that the sum of its angles, that is the measure of A plus the measure of B plus the measure of C, is 180 degrees. Okay, so we will give a paragraph proof. This starts with a construction, and there is no way to prove the triangle angle sum theorem without a construction at the start. So let us say through B, construct a line parallel to AC. And that's construction C6, which we talked about just a moment ago. Okay? We know that if we have a line and a point not on that line, then through that point we may construct a line parallel to the given line. And this is perhaps not a way that you've ever thought about a triangle before. You've never thought about a triangle as like lines and then points not on that line, but that's how you have to think about it. Think about the line AC and the point B not on AC. Now, I also could have constructed a parallel through, say, A, parallel to the line BC, or a line through C, parallel to AB. It doesn't really matter. It works out very much the same. But I did have to pick one. So through B, construct a line parallel to AC. And we will actually show this in the diagram. So through B, we construct a line parallel to AC. I will mark them as parallel, and I will also label some angles as well, which we may always do. Okay, now consider the relationship between angle 1 and, this is really quite a gorgeous proof. I think you'll be amazed by this. This is the best proof we've given so far. So consider the relationship of angle 1 to angle A. Those are alternate interior. Consider the relationship of angle 2 to angle C. Those once again are alternate interior, but the lines are parallel. And we have the alternate interior angles consequence, which says that when lines are parallel, alternate interior angles are equal. Okay. So that means that those angles are equal. 1 is equal to A, 2 is equal to C. Now, also, let us consider the sum of angle 1, angle 2, and angle Okay, I'll tell you what, I'll drop a little b beside it to make sure you're clear about that. That's the interior angle of the triangle B. Okay, what is the sum of 1 and 2 and b? Well, together they form a line. So this means that their sum is 180 degrees. Okay, together, and you'll allow me to be a little quick here, right? We actually have 3 angles instead of just 2, like in the linear pairs theorem, that together form a line. But no matter, just like in the linear pairs theorem, their sum will have to be 180 degrees. So together, angles 1, 2, and B form a line. Form a line, not lines. And thus it follows that the measure of 1 plus, dang it, it follows that the measure of 1 plus the measure of B plus the measure of B. Yeah, I'm just going to leave it. Plus the measure of 2 is equal to 180 degrees. But by the alternate interior angles consequence, it follows that the measure of 1 is equal to the measure of A, and it also follows that the measure of 2 is equal to the measure of C. And finally, we just simply substitute. In that equation, 1 plus B plus 2 is 180. We can replace 1 with A, because 1 and A are equal. We can replace 2 with C. For some reason, I wrote an S instead of a C, so let me go and fix that. So measure of 2 is equal to the measure of C. So in that equation, we can replace 2 with C because they're equal to one another. So thus by substitution, it follows that the measure of A plus the measure of B plus the measure of C is equal to 180 degrees. And there it is. There's the proof of the triangle angle sum theorem. And you might have been a little confused at the very start when I said that this chapter would be a study of parallels and that it would lead us to a proof of the triangle angle sum theorem. And I do understand that would seem mysterious because, of course, in a triangle, you don't have any parallel sides. So how could parallels be relevant? The way they become relevant is that you introduce the parallel. That is, you construct the parallel in. So now perhaps you begin to understand just how important constructions are to us. They are absolutely essential in some cases, like in this one. All right, now let's talk about some corollaries of tasty. That is, corollaries of the triangle angle sum theorem. What is a corollary? Well, it's just a theorem of a particular sort. What sort is that? Well, mathematicians call corollaries quick consequences, usually of theorems that are themselves significant. So if you don't particularly want to use the word corollary, you can absolutely do that. They're just theorems. But however, when you say corollary, you do indicate something about the position of a theorem in a theorem structure. You say that it's a quick consequence of some significant theorem you've already proven. We will have 5 corollaries of tasty. Okay, so most of these I won't take the time to prove with you. I think you are at the point now when you can prove them yourself. The first of the corollaries is the third angle theorem. It says that if 2 angles of one triangle equal 2 angles of a second, then their third angles are equal as well. And probably you can immediately guess about the structure of this proof. The sum of the angles in the diagram of ABC is 180. The sum of the angles of DEF is also 180. And then we subtract equals from equals, and we should get that C is equal to F. Next is the triangle exterior angle inequality. It says, and this is like the exterior angle theorem that we saw before. It's a stronger version of it, actually. It says that a triangle exterior angle is equal to the sum of its 2 remotes. Before we said that an exterior angle is greater than either of its remotes, and that is absolutely true. Now we say, make the stronger claim that says the exterior angle is actually equal to the sum of its 2 remotes. So consider the diagram. We have triangle ABC, in which side AC has been extended to create the exterior angle BCD. There it is. So what we wish to prove is that BCD is the sum, actually, of angles A and B. And how will that be done? Well, let me give you a sense of this. What's the relationship of angle BCD to angle BCA? Well, clearly they're a linear pair, which means that they are supplementary. But then consider the relationship of angle BCA to the sum of angles A and B. Well, that relation must be that angle BCA is supplementary to the sum of A and B, because supplementary merely means sums up to 180 degrees. So what then follows, of course, is that BCD and the sum of A and B are supplementary to the same angle BCA. And we know by the same supplements theorem that measures supplementary to the same third measure are, in fact, equal to one another. So I'll let you write that out. Okay, so the acute angle corollary. It says that every triangle has at least two acute angles, okay? And of course, it immediately follows from that, to go back to our definitions, that an obtuse triangle has precisely one obtuse angle, and a right triangle has precisely one right angle, because the other two angles must be acute. So let us then consider the proof of this, that every triangle has at least two acute angles. In particular, if we're given a triangle ABC, that at least two angles of ABC are acute. Now, before we actually give the proof, we have to pause and talk about another innovation in proof. We talked about paragraph proof earlier, which is simply another way to arrange proofs. Now we must talk about another kind of logic that occurs within proof, another kind of proof strategy, and it's called indirect proof. To prove the acute angle corollary, we'll make use of this new technique called indirect proof. And the idea here is this, is that we'll make an assumption, we'll prove that this assumption leads to a contradiction, and then we'll return to that assumption and conclude that it's false, which should seem logically right. What do you say about some assumption if that assumption leads you to a statement that you know is false? Well, if it leads you inevitably to a statement that you know is false, that means that the assumption must itself be false. There's no way for a true statement to logically correctly imply a false statement, okay? So if some statement implies correctly a false statement, it itself is false. Here's an example, okay? Hopefully this will get the idea through. So let us say that we know that S is equal to X plus Y, okay? That's first part of the given. We also know that X is even, and we also know that S is even. Okay, so take a moment to make sure that you understand the structure of this. We are given that S is the sum of X and Y. We're given that X is even, and we're also given that S, the sum, is even. Now, what we wish to prove is that Y is even. We will do this indirectly. How does that come? How does that go? Well, let us assume that Y isn't even. That is, let us assume the negation of what we wish to prove and ask what follows from that. Okay, well, if we assume that Y isn't even, this means, of course, that it's odd. And then what that means is that S is now a sum of an odd and an even. We know now that the scope inside of this indirect proof that Y is odd, but we're told in the given that X is even, and S is the sum of X and Y. So S is now the sum of an odd and an even, which means, of course, that it itself is odd. Just sort of basic number fact, the sum of an odd and an even is odd. However, this contradicts what we were told. We were told that S is even. So the assumption that Y isn't even leads to a contradiction. It leads to a statement that we know is false. Then what do we have to say about the assumption, given that it leads us to a contradiction? We have to say that the assumption is false. But again, the assumption was that Y isn't even. So now we have said that it's false, that Y isn't even. That means that it is, okay? So there it is, indirect proof. It might seem a bit strange to you. It might seem a bit sort of convoluted, turned around, but it's actually an incredibly powerful proof technique that sometimes is absolutely necessary. And actually, I think that students are quite well acquainted with it. If you've ever in your life said something like this to somebody, you've done an indirect proof. What I mean is this: well, that can't be true, because if it were, then, well, what you actually did is you just started an indirect proof where you showed them that it can't be true, because if it did, it would have this consequence, which we know is false. Okay, that's indirect proof. All right. Now, as for how we'll actually structure, that is how I'll actually write out our indirect proofs, we'll always do this in we'll always do this in paragraph style. Okay, I know of no good way to organize indirect proof in column form. And when we write these out, we'll always use the word assume or assumption. Okay, so we'll say something like assume that. That always indicates to us that we're about to begin an indirect proof. After we've made that assumption, then we will show sentence by sentence that this assumption leads to a contradiction. And then once we reach that contradiction, we return to the assumption and say that it's false. That's how they always work. Okay, so let's go back now to the acute angle corollary and discuss its proof. So once again, we wish to prove that every triangle has at least two acute angles. Well, assume otherwise. That then marks the start of the indirect proof. Assume in particular that a triangle ABC has at most one acute angle. This, of course, means that ABC has at least two right or obtuse angles. Then consider the sum of those two that are right or obtuse. That sum is at least 180. But then when you add in the third angle, of course, then you will be over 180 degrees. But that, of course, contradicts the triangle angle sum theorem. Triangle angle sum theorem says that the sum of the angles of any triangle is always precisely 180 degrees. So what's just happened there? What just happened here? If we have a triangle that has 1 or 0 acute angles, it will have to follow that the sum of its angles is greater than 180 degrees, but that is impossible. So that means that our assumption is false, okay? But what did we assume? We assumed the negation of what we wanted to prove. And if that negation is false, then what we wanted to prove is true. So every triangle does indeed have at least two acute angles. Okay, so now for the right triangle corollary, that says in a right triangle, the nod right angles are acute and complementary. This is really easy to prove. We can make use of the previous corollary, right, that says every triangle has at least two acute angles. Well, the right angle isn't acute, so the other two must be acute. So that's part of this. And then, of course, the sum of the angles total is 180. And if we subtract out the 90 for the right angle, that leaves 90 for the sum of the other two acute angles. And of course, when their sum is 90, we say by definition that they are complementary. So I don't think you'll have any trouble with that proof. And then finally, we can now prove that each of the angles of an equilateral triangle measures 60 degrees. And this is really quite straightforward. We proved in a previous chapter that an equilateral triangle is equiangular. That is, if the sides are equal, then so too are the angles. But we now know that the sum is 180 degrees. So it will follow just by a little bit of algebra that given that all the angles are equal and their sum is 180, then of course each has to be 60 degrees. All right, now where we end up the chapter is with an additional pair of triangle congruence shortcuts. Okay, now the previous chapter was devoted to congruence, and there we had three shortcuts to triangle congruence. I hope you remember that they were side angle side, side side side, and angle side angle. Now we can add to that list of shortcuts, and we will add AAS, that is angle angle side congruence, and we will add HL, short for hypotenuse leg congruence. And the reason that they're in this chapter and not in the previous chapter is that we had no means to prove that they are true in the previous chapter. Now, here in the summary, we won't actually take the time to prove AAS and HL, but it could be done. And the proofs of both of those ultimately will make use of the triangle angle sum theorem. So if you're curious about this, you can look at the chapter on parallels. I guide you through the proofs. Okay, so here's angle side stated. It says that if two angles of one triangle equal two angles of a second, and a pair of non-included sides which correspond are equal, then the triangles are congruent. That should really come as no surprise, I think, given the abbreviation AAS. AAS says we have a pair of angles equal. Then as we work our way around the triangles, we have another pair of angles equal. And then as we continue to work around, we have a pair of equal sides as well, where the equal sides are not in between the included angles. If we have all of that, then the triangles are congruent. And of course, we would like to have a picture, so here it is. So we have two triangles, ABC and RST. I have angle A in one equal to angle R in the other. I have angle C in the first equal to angle T in the second. And then I have side BC equal to side ST. Okay. And notice that those equal sides are not in between the equal angles. The included sides, that is the sides in between, are AC and RT. That's not what we're given. And instead, we're given that BC is equal to ST. And notice as well that those sides correspond to one another. And how can we know that? Well, both of those sides lie opposite the angle with a single hash mark. So this is an example of angle side, and it will follow by angle side that the two triangles are congruent. Now finally, hypotenuse leg. As perhaps is no surprise, the word hypotenuse signifies that we have right triangles. Okay, so here's HL stated. If we have two right triangles and they have equal hypotenuses and a pair of equal legs, then those triangles must be congruent to one another. Okay, so here's a picture. I have two right triangles ABC and DEF. The right angle of the first is at C. The right angle of the second is at F. Okay, so if we have these right triangles and their hypotenuses are equal, that is if AB is equal to DE, side note, the hypotenuse is the side opposite the right angle. You probably knew that. And, let me continue, the legs BC and EF are equal, then it follows by hypotenuse leg that the triangles are congruent. So again, if I have two right triangles with equal hypotenuses and a pair of equal legs, then those triangles must be congruent. And we have one final proof to give, and that's proof of the converse of the isosceles triangle theorem. Okay, you of course remember the isosceles triangle theorem. It says that if a triangle has a pair of equal sides, that it also has a pair of equal angles, and in particular, the angles opposite the equal sides are equal. Here we reverse that because that's what you do with converses, right? So here we're given a triangle with a pair of equal angles, and we wish to prove that the sides opposite are equal. Yeah, that's the converse. Okay, now we can do this very much like we did the proof of the ITT. So it will start with the construction of the angle bisector of B. Okay, so let us do that. I'll draw it and then I'll write out what I've done. So I will construct, the angle bisector of B. Sorry, I can't get my pen to work. So there we go. I will construct the bisector of angle B. That will go to a point D. Okay. Angle bisector means, of course, it will have a pair of equal subangles. And I tell you what, I will call those angles 1 and 2 for the sake of simplicity. Now, when we add a construction to a diagram, we need to say that we have done so. So construct the bisector of angle B. Okay, and we know that's one of our allowed constructions, so we have now done that. Okay, and I'm going to do a paragraph proof. By definition of bisector, and notice here that, like I said when I introduced paragraph proof, just because we write our proof in paragraph form doesn't mean that the standards have changed. We still have to provide justification for the statements that we make. In this case, the justification is the definition of bisector. So we know that the measure of 1 is equal to the measure of 2. And now think about the two triangles that are present in the diagram, triangles ABD and CBD. Okay, I have angle in one, angle A in one equal to angle C in the other. I have angle with label 1 equal to angle with label 2 in the other. And then, of course, I also have a side in common, which is BD. And what that means then is that the triangles will be congruent by angle, angle, side. So let us note that BD is equal to BD. Ooh, what a mess. That BD is equal to BD by, you've seen this many times, haven't you? By reflexivity. And thus, by angle, angle, side congruence, it follows that triangle ABD is congruent to triangle CBD. I'll leave that one. And then we're almost done. I suspect you know what's about to happen, right? How do we ever in this class prove that sides and angles are equal to one another? Well, almost always. We prove triangles congruent and then CPCTE. So let us finish with CPCTE. And then by CPCTE, which again means corresponding parts of congruent triangles are equal, it follows that the measure of A is equal to the measure of C. Okay, and with that, the proof is complete. And it might be instructive here as we finish up to compare this to the proof of the ITT. Okay, in the proof of the ITT, we dropped in the angle bisector as we did here. Then we proved triangles congruent by SAS, and then we used CPCTE to get a pair of equal angles. Here, we dropped in the angle bisector, and then we proved two triangles congruent by angle, angle, side, and then we used CPCTE to get a pair of sides equal. Oops, oh, look, sorry. I'm just realized that I did something wrong, and you're probably all confused. Sorry. I've talked for such a long time that I'm no longer careful. we already knew that the angles are equal. Now, it does follow, of course, by CP/CTE that the measure of A is equal to the measure of C, right? Because it follows by CP/CTE that all sides and angles that correspond are equal to one another. But that's not actually what we wanted to conclude. What we wanted to conclude is that AB is equal to BC. I'm sorry about that. So now the proof really is done. We have gotten where we wanted to go. We now know that AB is equal to BC, and the proof is complete. All right, and that's it. That's the end of the summary.